when I'm in France, French people occasionally tell me that my surname, Eads, reminds them of fighter jets and ask me if I work in fighter jets. And no, it's just a name. When I read your name, when I was looking at the schedule and met you, I was thinking you might be a Python programmer from your surname. This is Dr. Frederic Py. He comes from the Monterey Bay Aquarium Institute. He's actually a C++ hacker, so I think we'll have to have a beer. He's going to talk to us about sort of decision support and autonomous systems. He has a robot that scans the coast, and that's all I know about his talk. So without further ado, I'm going to start.
Okay, thank you. So first and foremost, I'm not from the machine learning community, so I am the over exception. I'm actually more from the automated planning and plan execution for robots. The big thing is, so ocean domain is something which where there is a lot of sensor data coming through. My planner needs symbols, and the scientists don't really care about the sensor data, but what they do represent. So there is really a strong need about that. About really do this mapping between the concept and the thing. So what I'm going to present you here is more a bunch of problems, few things we did quickly with machine learning and very basic machine learning in situ for the robot in order to be able to sample data, and also further down the road what we're working now in this kind of more having a network of assets, both static and moving assets, and trying to really sample the ocean in a very targeted manner, and which can be interesting problem for your community, and which we are interested on. So first off, what is MBARI? So it's Monterey Bay Research Institute. We're a close neighbor from Berkeley. It's the Monterey Bay. Actually, here is just 70 miles south of San Francisco. And MBARI is right there. It's this building over there. So we are right by the sea. And an interesting aspect for us, for ocean science, is there is this huge canyon in the bottom of Monterey Bay, which means that when people are deploying, it takes them only an hour or two by boat before being at deep water. And also the Monterey Bay is probably the part of the world in the ocean where there are the most assets sampling at any single time, because there is not only this institute, there is a bunch of other with static and dynamic assets, which are really sampling all year long and collecting data. So this institute is funded by David and Lucille Packard Foundation. So, and it's kind of a mix between ocean science and engineering. It's really, there is this thing where both are working hand in hand to provide new technologies for science, and also science is giving feedback on what are their needs and what kind of they foresee as interesting problem for the future. So yeah, we have a bunch of assets. So there are 2 boats right now, and the Zephyr is going to be replaced. 2 autonomous underwater vehicles which have an autonomy of 18 hours, which is covering 80 kilometers in the bay overnight. And 1 long-range AUV which can navigate for something which is around a week or so right now. And all of them are equipped with a bunch of sensors about physical and chemical property of the ocean scientists can analyze. And this is mostly what we're going to speak about. So yeah, ocean science nowadays, so it's going at sea with a scientist on a boat and doing the sampling manually with all the internet, etc., costs a lot of money. So more and more you're seeing either static or mobile assets which are deployed in an area of interest because they can sample a lot of data autonomously, bring it back, and then the scientists can just focus on analyzing the data. They are still going out, of course, because some data cannot really be provided in a manner as good as when they are there physically, but it's really this community, because of budget issue and because of trying to stay as long as possible to sample the ocean, are using a lot of these assets, which are collecting data and really trying to give them a better view on how the ocean is working and what are the relations between biology, physics, and chemistry in this context. So there are many assets which have been developed. So buoys are just a fixed buoy with a bunch of sensors which are doing vertical profile, and usually they are sending back the data in a constant stream, more or less. Drifters are small floats you're dropping in the water and which are following current and allow you to stay with the water mass without using. And then there are also gliders and AUVs, which are more this kind of mobile assets, which are with a better level of control on where to go. And of course, there is satellite data, which they are using a lot to see the big picture on what's going on. But we have these assets, but at the same time, until now, at least, these assets were usually constrained on their ability to adapt and react. Mostly because dealing with the dynamic of the ocean and the problematic of extract meaning on board of the asset in order to readapt based on the scientific need was very challenging. And so they did separate the thing. And for example, the AUVs, when I came at Emory 6 years ago, there was a pre-designed set of waypoints. It was surveying this area and just building time series on a day-to-day basis. And then they were just doing slight adaptation based on their understanding in this long time series. And the ocean feature of interest for scientists are really, as I said, they are often expressed through complex relation between all the data we have. So, and I will show some example, but it's really, you have this thing, and quite often on top of that, the scientist doesn't have the perfect mapping about that, a mathematical mapping. It's more an overall high-level understanding, and if in order to do explicitly this mapping as a software engineer, it's usually a lot of back and forth with the scientist if you're doing it in a classical manner. And the target, the feature you are targeting are always moving. And in two very different ways. So first of all, it's physically, water is moving, it's following current. So when you see something, if you're coming back at the same place, it's probably not there anymore. And when you see something from satellite data, which is 4 hours old, it's in some aspect, if it is something very small, it may be at a totally different place when you deploy the vehicle. And there is also scientifically, because as their understanding improve, but also as the hot topic in the ocean science is evolving, they will have different targets. It's 1 year it will be we want to focus on front. The year after it's we want to focus on bloom patches and how they evolve. So you have these two aspects which are very challenging for engineering, because if you design an algorithm and the year after it's not relevant anymore, it will be problematic. And not only that, but actually nowadays you'll see more and more, as they did gather in the past this time series, they start to have a better understanding on what's going on and where to focus. So, which means that these vehicles are less and less meant to build this static long-term time series, but more and more trying to follow a specific feature of interest. So yeah, in the past it was a repeated waypoint-based surveys with waypoints being defined by their latitude and longitude. And they were limiting to just sensors which were giving just physical and chemical properties. The focus is now really moving to things where understanding how this physics and chemistry impact biology. Understand also trying to track the lifetime of biologic population in a certain water mass. So, for example, what provokes a reptile to bloom or to disappear? What is the evolution of different populations in this bloom patch? And also, the scale of the interest really narrowed down. It's, they are speaking more and more of mesoscale, which is order of few kilometers in the ocean, and try to focus on a water mass at this scale and follow it through, for example. But then there is a problem, it's how do you define a water mass? So to see you, so the one of the assets we are using, and part of this evolution too, which is to better understand this thing, is, so here is a Dorado Galbary UV. So it's something which is around 8 feet long. And so it has a delta, it's flying at roughly 1.5 meters per second. And with a bunch of sensors, there is something like 10 different sensors, yeah, okay. And which are sampling multiple data all on their own. And on top of that, what was added 5 years or 6 years ago are these syringes, which are called the gulpers. And the objective is, there are 10 of them in the vehicle, is when something of interest happens, is collect the water, and it takes roughly, it's relatively fast, it takes 3 seconds to collect the water, so it can be brought back to the scientists and they can do further analysis such as genetic analysis and things like that. The big question that came 5 or 6 years ago is how to trigger these things in a targeted manner. And this is, this is roughly when I was hired and I roughly explored this thing. But there are also other people who worked on different algorithms. One approach, which is just looking, so there is a sensor which is giving the chlorophyll fluorescence of the water. So it's looking at the chlorophyll fluorescence of the measurement, and then it exploits the fact that the data, when it's sampling, so you have a view of, interpolated view of the sampling of the data, it's going up and down in a yo-yo manner. And basically when it detects the peak, chlorophyll peak on the first yo-yo, it will plan for the next, for this area to sample the thing. And they are taking, so the black circle represent where it was sampled inside, and they are also using 2 white samples which are sampled outside to have some kind of comparative view of the problem. INL is a thing which I worked on. So the INL is this kind of thin sheet of suspended material where there is no, so this is chlorophyll fluorescence, there is no organic activity, it's more the dust from the bottom, if you wish, which is rose toward through upwelling, so through a push from the bottom, and which will bring nutrients to the organism. And there is an interest on looking either inside the INL, or which is not shown here, when it connects with the chlorophyll fluorescent layer to see what is the impact in this aspect. And this problem is multidimensional, and I will develop it a little further. It's not one single sensor data as opposed to chlorophyll peak. It's a set of sensor data which are collected and how they relate one to another. Other problem they are looking at, and they are looking at right now, actually, there is an experiment at the end of this month, which is the front. So the front is, so this is the temperature of the water in the survey, and you see here you have stratified water with very warm on top and very cold at the bottom, and then you have the water which is much more uniform along the water column. And at this frontal zone, there is usually a lot of biologic activity, and which is different depending on which side of the front you're looking at. So these are the problem, and they are all very different in many aspects, and I will hopefully develop it. There are also new problems which are coming. It's ammonium has a huge role in biology. Big thing is we don't have an existing sensor that can be used on the vehicle right now. So they want to sample in the ammonia, but we don't have things. But there is hope, especially for someone looking at machine learning. It's when you're looking at the temperature and salinity and the ammonium measurement they did physically with from a boat, you kind of see there is not that much quantum utility, so you see a cluster over there where the ammonia is higher. So I'm going to go faster. And there is also specific population which are not looking. So going back to the INL, intermediate nucleoid layer. So this is the data that was presented to me without the labeling thing, and they were telling me we want to sample this part. But when I was starting to interact with them, it was kind of finer grained than that. It's first off, so here there are multiple missions which are put all together, and it's as you can say. So the green part is where they wanted to sample initially. It extends a lot and it overlaps with other areas they did define. And it's yeah, at the bottom it's the way I did ask them to label the data. And if you're looking here, for example, so there is this thing which is fairly similar, but for them it's not interesting. It has the same chemical property, but the altitude is too close from the bottom, so they didn't care about that. And to do that, I just used a simple sum learning at first, where basically I was using some sensor data and a combination of them as an input vector, plus some labeling, which were I was considering as a probability distribution. And as scientists weren't able to label the full data because there are a lot of time where they don't fully know and they don't have also that much time to label this thing, there is a lot of data. I think that I had less than 10% of the data which was labeled. And so it's really, I did something which is kind of semi-supervised learning from some, and then from the sum I extracted cluster. The approach had nothing really formal. It's just me hacking my way through. And we did apply it to both INLs in survey. So you see there is a survey here. And also initially in another problem which was trying to look at the nitrate which is injected from the bay. And for both of them it worked very well, but it was also bringing a lot of problems. So it was a proof of concept, and it was working well enough that scientists were happy about it, but there is still many challenges. I discovered labeling was really, really difficult, and both because scientists don't have necessarily a full understanding of this problem, and the relevant data we have is often sparse. Yeah, for example, here it's an analysis of all genetical analysis of all the Gulper sample which were taken in October. And there are only 10 Gulper samples. So from all the points you have, which is 300,000 sensor data for each sensor field, you have only 10 full label you can fully trust on. And yeah, quickly, so because I'm already over time. Beyond that, so it was just in a single vehicle, but now we are looking at, so it's the Canon initiative, which is, I don't remember, Agile. So it's an ocean network, and the objective is really to have all the assets and the scientists being able to interact with them. And the goal is really to understand these big cycles. So who is eating who, where is CO2 going, and how these things are evolving. And so it's really trying to put much more the scientists inside the loop of the vehicle, even though they are not there, and really gathering all the data and trying for data from multiple sources, trying to do both historically and in real time this aspect of notifying users when something which is interesting for them, still with this notion of mapping sensor data with a scientific concept, and also allows them to either themselves readapt the mission, or even more so being able to anticipate this kind of thing and retarget the vehicle dynamically in this example in the bay. And there is this closed full loop, and I will stop there.
Thank you very much. As a machine learner, I find it very encouraging when I see people from new fields I haven't sort of encountered before sort of try out machine learning. I think that's very encouraging. And I think it's great to have oceanographers here and people from other fields here. So any questions for our speaker here? Questions?
Just a quick general question. In astronomy, there's a concept called the virtual observatory, where all astronomical data is kind of brought together in a coherent way. Is there any analogous thing for oceanographic data or Earth sciences data in general that's parallel to that?
Well, it's not that much, and even more so because there is, for example, the change of support for them. It's what you're seeing from satellite, which is roughly this big picture, is not what you will see on the vertical profile of the vehicle. And there is all these problems which have not been answered. And I don't even speak about practical problems where nobody is really using the same kind of representation and protocol to deal with that. So that was actually a lot, and Daniel maybe able to speak a little more. A lot of work to try to bring this thing together, at least inside our institution, or when people are bringing those machines. It's a big challenge too, because even when you have multiple sensors bringing just a single data source, it can be very challenging too, such as temperature. And temperature is actually no brainer. It can be challenging to make sure that everybody is distributing the data in the same manner. Did that answer your question?
Yeah. Any other questions?
Yeah, I'm sort of curious. So, along the same lines, very interesting talk. So, do you have anything developed along what are all the interesting things you've already done, and what are the open problems where more machine learning can be helpful, right? I mean,
yeah. So I showed the thing about ammonia. It's really this aspect. It's right now. So I know that someone at Embry is working on a physical sensor, but it's really, so it's by September, it will be a strong focus on the experiment, and they plan to use AUVs to do that. But right now, there is no real sensor that can provide such data. There is also the thing about time series and being able to predict a model, predict a little ahead what's going to happen next, either inside the vehicle or not, is an interesting problem. And then there is really all this data coming from different sources in more this context, which is something we are wanting to exploit. How these data relate one to another, but also, and I didn't speak about that, I'm personally interested to explore how I could extract, for example, because we have this system where people can converse around the data and trying to really learn what tags are associated to this data based on the conversation, for example.
One related question for sign-off. If you think of active learning, right? What are the data points that can be useful in this context? Is that something that crops up at all? This stuff seems to me there's so much going on. You've got deployment, but then you figure out which data is useful to you and not as you learn, right?
Yeah. Right now, what we did was mostly offline and having something where as the data is coming through, trying to learn, okay, this thing looks something interesting. I don't necessarily know what, or maybe I know, but it's really being about, and it's interesting also because I didn't even speak about this, the communication we have between the vehicle and the shore is very, very sparse. So having the vehicle able to identify what data is important to communicate will be very interesting too.
I'm sorry we're running a bit short on time, so thank you very much. Let's thank our speakers.
Automated planning and plan execution for robots. The big thing is, so ocean domain is something which where there is a lot of sensor data coming through. My planner needs symbols, and the scientists don't really care about the sensor data, but what they do represent. So there is really a strong need about that, about really do this mapping between the concept and the thing. So what I'm going to
Institute. He is actually a C++ hacker, so I think we'll have to have a beer. He's going to talk to us about sort of decision support and autonomous systems. He has a robot that scans the coast, and that's all I know about his talk. So without further ado, I'm going to start.
Okay, thank you. So first and foremost, I'm not from the machine learning community, so I am the other exception. I'm actually more from the automation.
When I'm in France, French people occasionally tell me that my surname, Eads, reminds them of fighter jets and ask me if I work in fighter jets. And no, it's just a name. When I read your name, so when I was looking at the schedule and met you, I was thinking you might be a Python programmer from your surname. This is Dr. Frederic Py. He comes from the Monterey Bay Aquarium
manner, and which can be interesting problem for your community, and which we are interested on. So first off, what is MBARI? So it's Monterey Bay Research Institute. We're a close neighbor from Berkeley. It's the Monterey Bay. Actually, here is just 70 miles south of San Francisco. And MBARI is right there. It's this building over there. So we are right by the sea. What to present you here is more a bunch of problems. Few things we did quickly with machine learning and very basic machine learning in situ for the robot in order to be able to sample data. And also further down the road, what we're working now in this kind of more having a network of assets, both static and moving assets, and trying to really sample the ocean in a very targeted